and gas and a bunch of mainly nothing. Oh hey, look at that. The rocks are going around the gas. Hold on, what the heck is going on here? To understand, let's look at a bit of physics. Well, did I say a little bit? To find out what kind of magic this is, we'll have to go back in time. Okay, not that far. Stop. Yes, that's perfect. This is gravity guy, but most people call him Isaac Newton. One thing he said is that force equals mass times acceleration. Now, what do all these words mean? Force is just a push or pull on something. Mass tells you how much of something there is. It's also a measure of inertia. We'll get to that later. Acceleration is the derivative of velocity with respect to time. That's too many big words. Let's say it's how fast velocity is changing. The key takeaway is that if you apply force to a fixed mass, you get a predictable amount of acceleration. If you know all the forces acting on a basketball mid-air, you can predict 100% certainty if the ball will go hoop or in your neighbor's windshield. Whoa! Did the apple just fall on my head? Yes, Newton. It did. That must have happened for a reason, said Newton as he discovered that two masses attract one another, making an apple fall. Yes, even you, no matter how ugly you are, you attract pretty much the whole universe. At least a little bit. Hey, can you put that on paper? Yep, said Newton, who gave us the law of universal gravitation. In other words, how much two bodies pull on each other given their mass and distance times a constant. Bigger mass, bigger pull, bigger distance, smaller pull, actually a lot smaller pull. You see, as the distance increases, the force gets smaller by the square. That, my friends, is the inverse square law. Gravity is also the reason why the planets in our solar system orbit around the sun. They get their initial velocity from the solar system, from spinning gas, and since there's nothing in space to stop them, they'll keep moving. That's Newton's first law. The sun is so massive that the force of gravity keeps pulling the planets towards the sun, but the planets are fast enough to essentially fall towards the sun, but miss it, and this goes on forever, creating a round orbit. Actually, it's not round, it's more egg-shaped, and Pluto's orbit is just a complete mess, but you get the idea. In this case, the gravity is what we call a centripetal force. One thing many people confuse is mass and weight, and no, they're not the same. Mass tells you how much of this blob there is, and weight is the force of gravity the blob will feel. To make things clear, your mass would be the same on the moon, but your weight would be different because the moon has a weaker gravitational force, meaning a weaker force acting on your mass. So really, you're not overweight, just on the wrong planet. Alright, enough about Newton. Let's break some stuff. If you've ever dropped your phone, it might look like this. What the heck? Why'd you do that? The answer is energy, you know. The thing that kids have after eating gummy bears, energy has a unit joule. And it's not like force, it doesn't have a direction, it's just a number that's kind of chilling there as a property of a thing. You see, there's two main kinds of energy: kinetic energy, potential energy. In plain English, energy of movement and stored energy due to some circumstance. For example, when you held your phone, it stored gravitational potential energy due to being held above the ground at a certain height. Once you dropped it, the potential energy was converted into kinetic energy as the phone fell. Then it smashed into the ground and the phone absorbed some of the energy, making the screen go boom. Work is defined as the force applied over distance. For example, if you lift an apple by 1 meter, you would have done about 1 joule of work. This happened by converting chemical energy stored in your body to gravitational potential energy stored in the apple. As you might have noticed, energy and work have the same unit joule. So they must be the same thing. No. Energy is the total amount of work that a thing could possibly do. Work is just the stuff that actually happened and required energy. You know, force applied over a distance, which most people implies converting energy from one form to the other. If you try to lift a weight that's too heavy for you, you'd feel like that took too much work, right? Well, yes, but your feelings are invalid in the face of physics. Mathematically, no work has been done because work is a force applied over a distance. And since you didn't move the weight at all, no distance means no work. The key thing to remember about energy is that it cannot be created or destroyed. It can only be converted. Also, the conservation of energy. But a car that's moving has a kinetic energy. The car creates heat as a byproduct. The heat is then dissipated to the surrounding air, and that makes the molecules in the air move faster. And things that move have kinetic energy. So ultimately, the kinetic energy is transferred from the car to the air. With this knowledge, we can define the temperature as just average kinetic energy of atoms in a system. All atoms just in molecules like air wiggle like this. The faster they move, the hotter the things get. That's temperature. Let's talk about thermodynamics. It tells us that jumping in lava is probably not a good idea, but it's the absolute mess that is entropy. Literally, it tells you how much disorder there is in a system, indicating the number of possible states a system can be in. For example, get an ice cube. No, not that one. Yes, that one is perfect. Then you put it in the sun. The sun will obliterate the ice and turn it into water. Look at the structure of ice and water. We can see the ice is more neatly organized than water, which kind of goes all over the place. Also, water could look like this or even this, but ice will always look a little like this. In a total system, went from low entropy to high entropy, meaning more disorder and more possible microstates. The trend applies everything. The whole universe is on an unstoppable path to higher entropy. It's also the reason why time seems to go only forwards, or at least that's what we believe at this point. Practically, entropy tells us that some forms of energy are more useful for doing work than others. Burn some gasoline and your car will move, spitting out gas and heat. The heat and gas is pretty much gasoline, just in the form of higher entropy. As you can imagine, the stuff won't really make your car move, but the gas won't. Spontaneously turn back into liquid gasoline, meaning the form of gasoline with lower entropy is more useful for doing work. Okay, if you put some water in the freezer, will it not decrease in entropy? Yes, but the fridge is not an isolated system and will heat up the room more than it will cool down the water, increasing the total entropy. When I see some magic, whoa, what just happened? Some electrons apparently moved through some wires and let there be light. What's going on here? Objects have a fancy something called charge. It can be positive or negative, or if you have the same amount of both, an object is neutral. Electrons have a single negative charge. The flow of electrons is called electric current. To describe it, we use three parameters: current, voltage, and resistance. Current is the amount of electrons passing through a wire, and voltage is what pushes electrons to move. Simply put, the difference in electric potential. So you can imagine it as a slope that goes from high potential to low potential, where the flow of current goes downhill, and resistance is pretty self-explanatory. This is Coulomb's law. Wait a minute. This is just Newton's law of gravitation in disguise. This tells us that electric charges attract each other in similar ways as mass does. Opposite ones to cuddle, while the like charges literally couldn't think of more disgusting thing to be than what being with each other. These are four equations explain pretty much all of electromagnetism. The first one states that if there is an electric charge, there will be an electric field, or the big E, emerging from it. Add another, if you can, an electrostatic field. These lines tell us which direction a charged particle would feel a force at any given point. The second one tells us the same for magnetic field and even for electric charges. Are cool and can be alone. Magnetic poles are not. They're lonely. They'll always have a north pole with a south pole, and a single pole can never be alone. Okay. Same way, magnets only affect each other. Magnets, well, that's only true if they're not moving. The third and fourth Maxwell equations tell us that moving magnets create an electric field, and a moving charge or electric field creates a magnetic field. One consequence of this is that current can seemingly come out of nowhere by moving a magnet and to a next conductor. The moving magnet creates an electric field which makes the electrons inside the conductors go crazy. That is called induction. It's the reason why your phone charges when you put it on the charger, on the charging pad, even though it's not directly connected to the cable. In other words, electric and magnetic fields are so tightly linked that they are two parts of the same bigger thing. Let's say we have a charge. Since it doesn't move, it has electric static field. This sort of reaction that makes an electromagnetic field radiate outwards into space as an electromagnetic wave, depending on the frequency. The human eye can actually see this. It's called light, but most of the spectrum, it is invisible to the human eye and is used for things such as Bluetooth, wireless charging, and confusing human apes into thinking magic is real. The water molecules, what are they made of? The molecules are made of atoms. Atoms are made of core and some electrons. The core is made of proteins and neutrons, both of which are made of quarks. They are strange yet charming, from up top down to the bottom. Oh yeah, there's some more stuff, like for example the overweight brothers of the electron. All of this together makes up the standard model, which we believe to be the smallest things in the universe. At least that's the excuse we have for not knowing what the quarks are made of. Fun fact, depending on the number of protons in the core, you get different elements. Depending on the number of neutrons in the core, you get different isotopes of the same element, most of which are a little overweight and are very unstable, so fall apart into smaller atoms. That releases ionizing radiation. The stuff will kill you. Do not play around with radioactive atoms. If you have a large group of atoms, you can predict when half of those will have fallen apart. That's the half-life. Depending on how unstable an isotope it will survive a certain amount of time. So don't want to live. Some really don't want to live, but some live longer than you probably will. I did mention that light is the fastest thing in the universe, to be exact. 299,794.58 meters per second in a vacuum. That is pretty fast, said everyone. Also, light is a wave, said everyone. Why? If you shoot it through two tiny slits, it creates a fancy pattern due to interference, which is just a wave thing. You see, when two waves cross, they can add up or cancel each other out. These gaps are spots where they cancel each other out. In this case, light behave like a wave. Everything you know is probably wrong, Einstein said, smoking crack after hearing about the photoelectric effect, discovering that light comes in tiny packets called photons. Anyway, he said, as he continues, drop an absolute bomb on the entire field of physics, which is the theory of relativity. He assumed that speed of light is constant because it arises from two other constants. He also assumed that the laws of physics are the same for everyone, regardless of if it's moving fast or at rest. Now think about it. If two people turn on a flashlight, but one person is standing still while the other person is moving, wouldn't the person standing on the train steal the other person's light as going faster than the speed of light? Reality is no. It would be the same as their own flashlight. That's impossible except if time passes slower for that person from the perspective of this person. In other words, if the speed of light is constant, time must be relative. Also, gravity is not actually a force. Sorry, Newton, but rather a consequence of masses. Bending space-time. Einstein thought that the universe is a mesh of space and time, and everything and anything with a mass bends this fabric. Also, all objects move freely on a straight line when moving through space. Gravitation is simply the result of objects following these bent lines which appear straight to them. If you have a hard time understanding this, you can imagine two people on Earth walking in a parallel line on a short distance. The straight lines will never meet. Now imagine one standing across the east coast and the one on the west coast of the US. If they both walk north, eventually they will meet on the North Pole because the curvature of the Earth, they ended up on the same point even though they both walk straight relative to themselves. Tiny particles can release a humongous amount of energy by giving up just a fraction of their mass during fission. So, what is fission? It's the same thing Oppenheimer used to make things go boom. You see, there's two main ways to gain energy from changing nuclear fission and fusion. Fission aims to split the two nucleus of an atom into two or more smaller nuclei, which is most often achieved by blasting the core with neutrons. Fusion is the complete opposite, where you combine two smaller nuclei to get a bigger one. The energy came from something we call a mass defect, where the result of nucleus is lighter than the starting nuclei. This missing mass is what converted to energy during fusion. Fission and fusion are cool, but you have to be careful because you might just blow the planet. Light is a particle. Einstein accidentally discovered a whole new field of physics which he thought was just giant hoax. Quantum mechanics. That stuff is crazy. Another German guy called Max Planck said, yes, Einstein, you're right. Light does come in tiny packets. Actually, all energy comes in tiny packets or quanta. He is the daddy of quantum mechanics. Want to know where the electrons is inside an atom? It's here and here and everywhere at the same time. Actually, that's superposition. It's not in one state, it's in multiple states at once, at least until you measure it. Then it chooses one cozy spot to be in. Schrödinger gave us an equation that gives you a probabilistic model of where you can find it if you were to measure. Speaking of observing particles, they are also super sensitive about their private data. Look at the two images of a flying ball. In one, you can clearly see where the ball is, but not in which direction it's moving. In the other, you can see where it's moving and approximately how fast, but not where exactly it is at the moment. That is essentially Heisenberg's uncertainty principle. You can never know both the exact position and the exact speed of a quantum particle at the same time. Okay, let's recap. A small thing can be a particle and a wave at the same time. When you try to look at them, weird stuff happens. But you know what? It gets even weirder. Think back to the double slit experiment. We know that a light beam acts as a bunch of waves and we get interference. But here's the weird thing. Even if you send individual photons after sending enough of them and detecting where they end up, you get interference. Like how can that be? Well, it interfered with itself because it acted as a wave and went through both slits at the same time. That's superposition. Okay, well, that's just a measure of which slit it goes through. Once you start measuring which slits the photon goes through, it acts like a wave and the interference patterns disappears as every particle chooses just one of the slits to go through. Kind of sounds suspicious to me. Anyways, all this knowledge is going to cost you one to subscribe and a thumbs up. Thank you very much. And you can decide if maybe you'd want a tip with a comment, perhaps.